So what we're looking at here is normal distribution and where we're going to use this in our real life. The other word that we usually use for a normal distribution is called the bell curve. And different places that you'll see this in is if there's something that has multiple outcomes that could be different, points scored, time, lengths, all that. And it usually comes up as a middle ground, some average. Uh, More than likely you're going to get a bell curve forming. So an example of this would be when you're driving to school or work and you're driving. If you time that every single time you go, what's going to happen is that you're going to find small differences here and there. Some days it's going to take you 5 minutes, other days it's going to take you 8 minutes. Some days it's going to take you 6, other days it's going to take you 4. It's going to be moving around. If you get enough data points and you put them all together, what's going to happen is you're going to find your average, which everybody knows how to find the average. You find the sum of all of them and then you divide it by the total number. That's going to be at the middle, but on each side you're probably going to have an even number on each side of that sloping down. Some days it might take you real quick. It might take you 3 minutes to get to work. Other days it might take you, 10, 12 minutes. You might hit traffic or something. Somewhere else that you may see if you've ever been sick and you stay home, around like 10 o'clock, it's The Price is Right. Come on down. Bob Barker, all that good stuff before Drew Carey. But their game on there, Plinko. If you were to take Plinko and you drop that Plinko token, and you drop 100,000 of them from the very middle in the same spot, and you keep dropping it over and over and over and over and over and over and over again, what's going to happen is that over time, a bell curve is going to be forming. The middle, there's going to be most of them will occur in the middle, and then it'll slowly fall down left and right. And then the ends are going to be the least amount. And the last one is if you're working something that does a lot of, makes a lot of material, pushes out a lot of, metal pipes or cups or anything, and it mass produces something, what's going to happen is you're going to have small differences in it. It could be a small change in the weight, it could be a small change in the length of it, but there's going to be a small change somewhere. And if you were to take all of them and average them together, you're probably going to get a nice bell curve. Okay, so that's what a normal distribution is. So what a normal distribution is, again, it's a bell curve, and as you see, the one that's most common will occur in the middle. That's going to be your mean, and it should also be your median. It's going to occur in the middle, and then from there, each side, it's going to slowly drop off. Okay, and the further away you get from it, the least likely it's going to occur. Now, with this, you can use for different things. Finding the probability of different things goes into the bell curve as well. There's a few other applications that you can use for the bell curve. When you take like your SATs or the ACT or any other standardized test, what happens is over time it's going to make a bell curve. Okay, if you get a lot of them, because that test is going to average out somewhere, and then you're going to get a lot of people that has really high scores and a lot of people that have really, really low scores. But overall, it's going to be a nice, curve all the way through. Okay. So, I mean, that's what the normal distribution, that's what it kind of looks like. All right, now there's certain things that you're going to need to know. Now, in a normal distribution, there's a couple of notations that you have to know. The first notation is capital M. Capital M means the median, okay, or the middle number. Then there's also this Greek letter mu, which is going to be the mean. Now, if it is a standard deviation or a normal distribution, not a standard deviation, those are different things. If it is a normal distribution or a standard curve, the median and the mean should be the exact same number. And it should be at the highest point of the curve. If it's not, then it's not a normal distribution, or it might be slightly slanted somewhere. But if it's in the middle and it's at the highest point, then it is the mean, median, and it is a normal distribution. Now the other notation that you'll see is sigma, which is your standard deviation. Okay. So the standard deviation, if you want to take it from the mean, let's say the mean is 10, and your standard deviation we'll say is 2. If we move one deviation to one side, okay, that's one deviation, that'll move you down to 8. You're also going to move the same deviation on the other side, which will move you up to 12. And then you can keep doing that over and over again and take multiple deviations. After that, we're down to 6, and then 4, and then we're basically at the end 14, 16. Okay. But as you see, we're taking a deviation. So you can move the deviation is the same for either side. Okay, and you can move it on both sides. Now with this, the distance away from the mean, or the deviation, which is usually what we measure in, there's two things with this. First, the empirical rule, which is very important for estimating if a bunch of data points are a normal distribution. And basically what it is the 68, 95, 99.7, or the empirical rule. What it states is that if you're one deviation away, so sigma away from the mean, so as you see here, from here to here, that's one deviation. From here to here, that's one deviation. 68% of the data fall in this range. So if you were to take all of the data sets, all the pipes that were made, all the times that you took driving to school or work, and you found all of them that fall within this range, one deviation from either side of the mean, it should be about 68% of the entire population, or the entire set. Okay, so 68% of the entire set should fall into this range. Now, two deviations will have 95%. Okay, so 95% should fall within two deviations from the mean. Okay, so as you see, we went from 68 and then we expanded it to 95. So as you see here, we've added about 27%. So we've added about 27% from the one deviation. All right, so each of those, 27%, half of that would be about 13.5. So about 13.5% fall from the between the first deviation and the second deviation. And now the last one, the third deviation, 99.7%, which basically means that all the data should fall within 3 deviations of the mean. If it doesn't, then it's not going to be a standard deviation. So this is a way of estimating, and it's a way of assuming that something is a normal distribution. Now, with this, it gets into a lot of calculus, finding the area under a curve with this for finding these numbers. But overall, this is what it is. Okay, so this is the empirical rule, or the 98, 95, 99.7 rule. So one deviation from each side, it's 68%. Two deviations on each side, 95%. Three deviations, 99.7, or basically all the data. Right, now the last thing with the standard deviation and the normal curve is the standardizing of your data. So standardizing of your data is basically saying, okay, I have a given point. So if I have my curve and my mean is at 10, one deviation is 3, the deviation is 3, and I have the point 8. Okay. The question is, how far away is that? In terms of your standard deviation. So the standardizing, or the z-score, tells you the distance from the mean in terms of the standard deviations. So you would say that 8 is this many deviations away from the mean. And to do that, your x will be 8, mu is your mean, and sigma is your standard deviation. So in this case, to find our z-score, we would go 8 minus 10 all over 3. And then we would simplify this. Negative 2 over 3 is equal to z. So that means z is equal to negative 0.6667. Okay. Now the negative means that it's below the mean, it's smaller than the mean, and a positive would mean that it's above the mean. But that means we're about 2/3 of a deviation away from the mean.